Hello out there in TV land. Mr. Ferris here for calculus. We're going to look at section 3.4. This graph, I give you a picture of myself, but the lighting's not the best. I don't think you want to see me anyways. Okay, reviewing a little bit. Back in section 1, we talked about points like right here, critical points, where the derivative was 0, horizontal tangent line, slope of the tangent line is a derivative, or there aren't any on here where the derivative was undefined. Section 2 talked about when you had 2 points that were the same, straight across from each other, the slope of the secant line would be 0. Therefore, at least one place in between the slope of the tangent line had to be 0. Doesn't have to be where the functional values are 0. It can be anywhere where they're the same. Same down here. Functional values are equal. Slope of the secant line is 0. Somewhere in between, at least one slope of the tangent line has to be 0. Could even take it from here to here. And actually, there's 2 places then where the slope of the tangent line is 0. That was Rolle's theorem. Mean value theorem, if you take these 2 points, draw their slope of the secant line, at least once in between the slope of the tangent line has to be parallel. Mean value theorem is just a broader form of Rolle's theorem. Sorry about the movement. Best I can do with what I've got here. Section 3. Talked about increasing and decreasing functions. If the derivative was positive, which means all these slopes here are positive, the function would be increasing. If the slope or derivative was negative, function would be decreasing. Section 4 deals with something called concavity, which deals with the curvature of the function. Bottom line is, everything we do is trying to find out as much information about a given function as possible, whether it's rainfall, stock market, grades, selling of a product, whatever. We take the data, we plot it, we try to find a function that fits it. Once we find that function, we can figure out all kinds of things with that. Highs, lows, where things change, and so forth. With section 4, what we're going to look at here now is not these highs and lows, but right in here, kind of, if you were to think of this as a spoon, it would hold water. Right here, it wouldn't hold water. This part, and actually all the way from here to here, is said to be concave up. Here to here is concave down. And then back up here, concave up. If you look on page 191, they actually define concavity. And again, sorry that I'm moving stuff around. Probably hard to follow this when I'm moving around. Concave up, the actual definition, the derivative is increasing. So here, where it's concave up, all these slopes are getting bigger. Concave down, the slopes are getting smaller. Doesn't mean they're positive, nor does it mean it negative. Concave up, the slopes or derivative is increasing. Concave down, the slope or derivative is decreasing. Now, how we test for that is using the second derivative. When we did the function was increasing, the derivative was positive. Now, to take the second derivative, if the second derivative is positive, the function will be concave up. If the second derivative is negative, it'll be concave down. But the actual definition of concave up, the derivative is increasing. How we test for that is use the second derivative. If the second derivative is positive, that means the derivative is increasing, which means the function is concave up. So on this sign chart that I have here, and again, it's not the best, watch how these are labeled. X, f prime of x, f of x. This is actually section 3. It's where the derivative was 0. Those were my critical points. At -7, the function, there's a horizontal tangent line there. At -3, there'd be a horizontal tangent line. At 0 and at 2. Okay, with those then, here the function's increasing, which means the derivative was positive, increasing. Here it's decreasing. Derivative would be negative, function's decreasing. Increasing here, decreasing, increasing. Also, just based on this, knowing the derivative goes from plus to minus, which means my function's going from increasing to decreasing, there's a relative maximum. Here, the other way around. The derivative is going from negative to positive, which means the function's decreasing and then increasing, has to be a relative minimum. Now the relative maximum there, because the function was increasing, now it's decreasing. Relative maximum, relative minimum at 2. Okay, now if we go to the second derivative, and we'll go through practice problems, but that'll probably be on an announcement in written form. I don't know if I'm going to do all of those on YouTube, but I have to do at least one here. Here is the sign chart for the second derivative. Watch again here. This is x. This is f double prime of x, the second derivative. Okay, on all this region from here to here, it's concave down. Now, part of it's increasing, part of it's decreasing, but it's all concave down, which means the second derivative would be negative. I didn't put it in here, but the actual definition, that means the derivatives are decreasing. All of these slopes are getting smaller. They start out positive, they go negative, or 0, then they go negative. The actual definition of concave down, derivatives are decreasing. How we test it, the second derivative will be negative. That's concave down. Here it's concave up. Second derivative is positive. Here it's concave down. Second derivative is negative. All the rest then concave up. Second derivative is positive. In between are called points of inflection, where concavity changes. Okay, there were all these, and I can't get everything in. Well, I guess I can back it out a little bit, but it's hard to see then. -3, -1, and 1 are where concavity changed. Changed here from down to up, here from up to down, here from down to up. Those are called points of inflection. Points of inflection, the second derivative will equal 0. First derivative equals 0 are these critical points where the slope of the tangent line is 0. What will be very confusing is when do we use the function, when do we use the derivative, when do we use the second derivative. Everything is designed to tell us information about the original function. First derivative tells us whether it's increasing or decreasing. Second derivative tells us whether it's concave up or down. Okay, now I'm going to flip this sheet over. And I think I put part of this chart up last class. You'll notice out here, first derivative, second derivative. If the first derivative is less than 0, negative, my function is decreasing. If the first derivative is positive, my function is increasing. If the first derivative equals 0, it's a critical point. Critical point's derivative is 0 or undefined, and it's a possible maximum or minimum. Doesn't absolutely mean it will be. Could be something else. Second derivative. If the second derivative is negative, it's concave down. And again, the actual definition of concave down, the derivatives are decreasing. Not the function decreasing, the derivative decreasing. How we test for that is use the second derivative. If the second derivative is negative, the function is concave down. That part where it goes down like that. The actual definition again, derivative is decreasing. If the second derivative is positive, function is concave up. If the second derivative equals 0, it's a possible point of inflection. Most of the time it will be, but doesn't have to be. Okay, also something that's in section 4. Something called the second derivative test for maximums and minimums. And it is in your text. I don't know the page. If I flip to the page, I'll move this iPad all over the place. But it is in there. If, two conditions here, if the derivative